Okay, so in the break, some people asked me, how does one actually compute this, this object here? It is difficult because, in a given order diagram, like planar diagram, you have to look at all possible choices of V4 and V3. Any number of cubic vertices, any number of Vati vertices. How on earth does one compute this? So of course, this is a difficult job, but I'll tell you examples of some theories where it can be actually done, simple theories, and it does teach us something. So this is some question that Rajiv here is very worried about. How does one compute AH of lambda? So so how to compute A0 of lambda? I'll say something about that. All right. So that's one. And secondly, I learned from Tuhin that the actual success in phenomenology, is somewhat marred by the fact that the number of quarks is not just n, but it's n times nf, where nf is the number of flavors. So if NF is comparable to NC, to the number of colors, then the number of quarks and the number of gluons are pretty much comparable. So the suppression of the internal lines that I mentioned here, okay, is not so easy. So that's about, but the kind of large N limit that I'm talking about here, I was just taking n going to infinity and NF was held fixed. So the number of flavors, if there are flavors, then that was held fixed. Okay. So Tuhin has promised me that he will send me a paper. So I would request Tuhin also to add that to the bibliography, which I will share. Okay, so what else did I want to say? Good. So now I will tell you about the, again, to continue with Witten's paper, the existence of one meson states from the large N diagrams. One meson resonances, absolutely sharp one meson states. How does one see that? Well, it's very beautiful, so I should just give one example. So let us say that you consider a JJ thing, and I'm going to draw only a planar diagram of some. So I'm taking, in case you want to read Witten's paper, I'm taking exactly his example, I think. Some internal gluon lines like that, okay? The external lines are quark lines. And of course, what you should do is to replace these by that. Good, now I'm done. And let me write the color loops. This is the I loop. This is, let's say, the J loop. This is K. This is L. And this is M. These are the colors that are running in this index loops. And let us look at intermediate cuts like this to see what all this QQ bar operator can mix with at large N. Okay. Let's look at this one. Okay. This cut, what are the operators that it encounters? So there's a quark with color J. Then there's a gluon with colors JK, right? Then there's another gluon with colors KL, and a quark, with color L. So I have not drawn the arrows here, etc., etc. You should do that, and you should convince yourself that this is the combination that appears. It's one gauge invariant operator. Okay, that's the important thing. If you take a planar diagram, then at any intermediate cut, you always have only one gauge invariant operator, never two separate gauge invariant operators. Okay. To contrast this with the following, suppose you have this one, bigger, this, and that. Like this, which in terms of like this. So let's say this is the I loop, this is J here, this is K, this is K, this is the L, and you cut it here. So again, you know, there's a QQ bar at ends at QQ bar. You cut it here. You will see that it has, sorry, it should, excuse me, it should cut through the quark. It will be QI, then AI, J, and Q bar J. Okay, and I'm not doing it right. Sorry. This is AIK, and this is the K. This is the kth quark, K color. Okay, so this is Q bar K. Okay, so I better be careful about drawing the. So this is the K index. This is the I index, and so on and so forth. And this is the L, and so on. So you get at this stage you get I, K, K, right? So that's what it is. And now from here on you get L again. So QL, and this is LI, ALI, and Q bar I. So if you do have an internal quark line, then it could split into product of two gauge invariant operators. But we know that this is already suppressed. So therefore, this JJ two-point function must have a spectral decomposition in terms of, and if we believe that the theory has only color singlet states, that color is confined, then it must be just one gauge invariant operator that is going in the middle. And I started with operators, let's say, of the same quantum numbers of a particular meson. Okay. No, so therefore, it can only have one particle poles. Okay, because there are no cuts here. Okay, it has to have one particle poles because there's only one particle that is propagating in the middle. I'm not saying here what that one particle is. Okay, so therefore, it must be of the form that I have said here. Why this AN is nothing but there's a certain amplitude. So I'm not writing for lack of time. Just look at that expression over there. So there is a certain amplitude. So I interpret this observation by saying that it should look like this, where the J creates creates a certain meson state, which I have labeled by N, and here is a propagator with some mass, I don't know about that, and then here it is the N G. Okay, so this is something that I have called AN. So now, so therefore, JJ must be of the form, okay, I'm writing it anyway here again. AN squared divided by P squared minus MN squared. Now see that, remember that JJ planar diagram was of the form N. So for this to have a smooth large N limit, no infinities, nobody blows up, nothing of that kind happens, then it must be true that AN must be of order square root of N. So that is to say, the amplitude for J to create the meson N for any little n. This little n is the label of the meson. It must be square root of N. And MNs should, of course, not have any N dependence, because if they do, then this will not have a smooth large N limit. So MNs are of order 1. I'm not going to have time to discuss the two-dimensional QCD paper here. If anybody is interested, I can tell you how that goes. So all these assertions can be proved in that one. Okay, and there's of course also the other paper of Grosnevo, which I'm going to explain in some detail because it's easy to explain. I'll see some of these, show you some of these structures, how that happens. So therefore, it tells you about the existence of, okay, also infinite number. So this has to be infinite number. So that's also very clever, because if it's a finite number of terms in the sum, then at very large n, it will go as 1 over p square. Okay, but from RG, you know that it should go as log of p square. Okay, so the only way that can happen is that if the sum is infinity. Okay, so therefore, there's an infinite number of mesons, sharply defined, it's a one particle poles. Okay, infinite number of mesons, each with mass which is order 1 in the large n limit, and the amplitude for creating those from the vacuum by the insertion of the current operator QQ bar is square root of n. Okay, good. So that's all we need for to go ahead with the computation of the 3 meson amplitude and so on. You should really read Witten's paper and to see the subtleties and the quality of the prose. All right. Good. So now let us look at the free current. Okay. So QQ bar, QQ bar, QQ bar, they can just contract as they are without any internal lines at all. Okay. Or they can do, these things are called fishnets and stuff, and so on and so forth. Whatever you do, as long as it's planar, it would be of order n. Okay, so this is n. So JJJ is n, of order n. Now, we have already seen that each j, okay, can produce a meson. Okay, so therefore, this must have an interpretation in the following way, that if there are there is a meson vertex, then this is how it should look like. So there is a certain AN here, there is a certain AL here, and there is a certain AE. So some nth meson, L, kth meson, etc., they are being produced. And of course, each such amplitude goes as square root of n. Therefore, but overall, it must be n, right? So therefore, the meson vertex must be 1 over square root of n. That's it. There you go. So the meson vertex is suppressed. So mesons would rather freely propagate, okay, rather than produce two mesons, okay, because it's suppressed by a factor of 1. You can go on doing J. I'm, I'm omitting some things here. There is a certain amplitude for producing two mesons together. Okay, so that also, this could also have interpretation in terms of that, where I have produced two mesons, but it will be suppressed by a factor of, it will be order 1. Okay, this will be 1. And because this is square root of n, this is square root of n, this must be 1. Okay, so the one insertion of a current producing two mesons, okay, is suppressed compared to the production of one meson. So it's order 1. Okay, so you can see that these things, and just one more thing. It's similar. So JJ is again a disk with 4 crosses, like that. So with arbitrary number of gluon things inside, no internal quark lines, because as I said, every internal quark line is suppressed by an additional factor of 1 upon n. So this will have possibly, suppose there is a quartic meson vertex. Then the square root of n, square root of n, square root of n, square root of n here, square root of n here. So for the whole thing to be n, what should this be? Yeah? 1 upon n. Why should the answer come from a faculty? Okay, it's 1 upon n. So therefore, a 4 quark vertex goes as 1 upon n. Okay, and so on. You can do it for any. Sorry, excuse me. A 4 meson vertex goes as a square root of the same paper. In fact, the second part of Witten's paper talks about baryons. I don't have time to do that. Now I will close this qualitative session, and I'll do some quantitative stuff to address the question of how one can possibly compute. So Witten's paper comes with 2 reservations. One is that, it may not, that last year there was a beautiful paper for him the last year, beautiful paper by Breza, Zixen, Parisi, and Zubair, where they summed planar diagrams in a simple theory. Okay, so that's this paper. This paper is absolutely basic. Breza, Zixen, Parisi, and Zubair, 1978. And similar techniques were used in 2-dimensional lattice gauge theory, which is also called the Gross-Witten-Wardia model. And let me just say very briefly how the Breza et al.'s work went. Okay? Yeah. Exactly. Then the large n limit, the mesons are free. Yeah. Oh, yeah, indeed. That is right. So if you have n equal to 1 million, then you can certainly, or I mean, just a minute, even n equal to 10, perhaps not n equal to 3, but n equal to 10, let's say, then you can compute what the corrections are. They have to be small corrections, that's all I'm saying. You can even do, 1/3 in some powers. If you can do the large n corrections up to, let's say, the n number of handles, or some 10 handles, and whatever number of things. Yeah, I mean, I can give you examples of my own paper where I have done these computations, where n is 10 in my example, which, and there, it's not really n, it's large n adjoint scalar QCD, and where, it can be done. It can be done. All these 1/n corrections, 1/n square corrections, etc., they can be computed, and yeah. So the thing that Tuhin mentioned to me in the break is that the flavors the number of flavors plays an important role. So all the suppressions that I'm talking about here, this was assuming that I'm taking larger limit, the number of colors going to infinity, with fixed number of flavors. So all these countings, it was in that limit. But indeed, you can do them. Okay. Is more, for example, the suppression of the internal lines will not work, right? It will not work when NF is compared to NC, let's say. The number of flavors is comparable to. You can do that, but then you have to be careful about the flavor, part, the flavor part of the group theory. Some bit of that is known, but yeah. All right, good. So, right, and yeah. So let me tell you which model this is. Breza, Jackson, Parisi, Zubair. This is like a gauge theory, but with no space-time. So the partition function is given by, I can even call it as d to the power minus trace of some v of m, and I'm going to take v of m to be m squared by 2 plus g over n, m to the power 4. This g is actually the Toft coupling lambda. Okay, but I'm not going to use lambda because I'm going to use lambda for eigenvalues right now. So this g is the scaled thing, and I'm going to look at this theory in the limit of n going to infinity and g fixed. Okay, so in other words, if you called this one g to this fellow g, then the limit that I'm taking is n going to infinity, g tilde going to 0 in such a way, g tilde times n to g is fixed. Okay. But I'll use this notation, g by n, demanding that g should be fixed. Okay, so just very briefly, this is an invariant gauge. This is the, the UN invariant action, because there's a trace here, trace m squared, trace m to the power 4. If you make unitary rotations of this is a Hermitian matrix model. This is a Hermitian matrix model. So Mij. Okay, I'm not going to use upper and lower now. We just so the Hermitian matrix model can be written, in terms of a diagonal. So let me not use Ij. Diagonal matrix and some universal. A Hermitian matrix can be diagonalized into these, and I'll call these fellows as in eigenvalues, okay, real eigenvalues. So now the integral over the matrices, okay, can be made into an integral over the eigenvalues. And because these guys do not appear in the action, right? These guys do not appear in the action. Therefore, this V, sorry, I should, okay, S of A. These guys don't appear in the action. Therefore, I should be able to integrate out these angles, and that leads to some Jacobian. That leads to some Jacobian, the famous Jacobian. That's a square of what is called the Vandermonde determinant of eigenvalues, and delta lambda is given by a product of I less than j. This is some completely antisymmetric combination product of eigenvalues, and the square of that is the Jacobian that comes in the thing. So therefore, in that language, it's just given by p this stuff and e to the power minus. Now this just becomes sum over eigenvalues, right? Because it will be just given by S of lambda I. Oh, let me write down. N lambda I to the power 4. Like that. And I'll write this one also upstairs. So first of all, I'll write delta square of lambda as the product over all lambda I over lambda j, in which I'm removing this restriction and calling it I equal to j. And I write this, okay, in the exponent, so it will become like I not equal to j log of lambda I minus lambda.
Meaning that these eigenvalues are not degenerate.
Eigenvalues are not, so basically what will happen is that there is a repulsion of these eigenvalues. So the coincident eigenvalues are suppressed.
But if there is non-degenerate eigenvalue, then this Jacobian is 0, right?
Those all will not contribute to the path integral. We can discuss this. That's an interesting question, but they will not contribute to the path. Okay, good. Now, what this is, so this is the part where the large N business comes out. Actually, let me do one more thing. Let me rescale this just for convenience. Let me rescale M by factors of n such that this becomes like m square by 2. You can call it m tilde, but and then g of m fourth. Okay, so let me call it. Okay, so m tilde square root of n times m tilde is m was. So with that understanding, I'm doing this for m tilde, and there will be a factor of n here. This will go away. This will go away, and that's it. Okay. Now you see that in the limit of, so the eigenvalues are just real numbers, and in the limit of, so there's a certain density of eigenvalues. We will see that the eigenvalues are confined to a particular finite thing. So in the limit of to a finite interval, in the limit of a very large number of eigenvalues, okay, the density of eigenvalues approximately will become like a continuous function. Okay, so that is the main insight. That let me define the density of eigenvalues. This is just a counting function, and in the limit of large N limit, this just becomes like a continuous function. I have to ignore many subtleties here. I can tell you later on. I can also point to the literature where you can get the points that I am glossing over. So, oh gosh. All right. So you can convert this the integral over the eigenvalues, therefore, can be converted with a possible Jacobian, which I'm ignoring now. So in the large n limit, you can ignore them. And then there's an action. Action can be written in terms of also the eigenvalues, in terms of the density of eigenvalue. How? Clearly, by definition here, this is the same as n times rho lambda, lambda squared by 2 plus g lambda to the power 4, right? D lambda. Is that clear? That it can be done that way. And this fellow, an additional factor of n has appeared because I have defined my rho of lambda in this normalized way, so that rho lambda integral d lambda is equal to 1, not n. Okay, so because of that, this additional factor of n that appears here. And now you have a double sum here, and that will become rho lambda prime log of lambda minus lambda prime. And there is an integral with the restriction that the point lambda equal to lambda prime should be avoided. Okay, so that's what it is. Therefore, this S here, it has a factor of n square, where, right, because there's an n square here, and there's an n times n, there's an n square here. So I get this thing eventually where S of rho is given by rho lambda v lambda, where v lambda is this, this object, integral, so it was a plus sign here, so I should have a minus sign because of the minus here, and it is rho lambda prime log of lambda minus lambda prime, like that. And now you just do large n saddle point. That's it. Okay. That's the point about this, these methods, is that you write in terms of some gauge invariant variables like rho of lambda. In this case, this is even invariant variables, rho of lambda, so that it becomes, this is like writing the theory in terms of mesons, okay, or some invariant objects. So then explicitly, the number of degrees of freedom, which were earlier in n, that appears here like n squared because of the Tuft scaling, it appears explicitly in front of the action. So therefore, now you do large n saddle point. Large n saddle point. So you're supposed to do del S del rho equal to 0. And so then that will give you V lambda is equal to rho lambda prime log of lambda minus lambda prime. And this log is not so nice. So what you do is to differentiate this equation with respect to lambda, and you get the famous Riemann-Hilbert problem, lambda minus lambda prime, right? So where you are supposed to take a principal value prescription to avoid lambda equal to lambda prime, okay? So this is a certain function of lambda, which is like a potential that is created by a charge density. Yeah. Yes, correct. Right. So now I'm doing this, therefore I should write rho naught of lambda. This is the saddle point value, and that is now, so this is something that is known. Sorry, I missed a factor of 2 because I'm differentiating a quadratic here, so there's a factor of 2 here. So this is half of the lambda, but it's some function of lambda. It's a known function of lambda, which has the g in it, and this problem is called the Riemann-Hilbert problem. It's a well-known problem in complex analysis. It's like given this is like a charge density, and this is like a Coulomb interaction. The charge density creates this potential. The potential is known. Can you derive the charge density? The answer is yes. It's a well-known problem in complex analysis called the Riemann-Hilbert problem. And let me just tell you what the answer is. The oh, sorry. Yeah, here it is. So explicitly, solution of this problem, explicitly it is given by 1 over pi 4. This is just to say that, you know, it can be explicitly computed, lambda square, and 4 is squared by lambda square, for lambda less than or equal to 2a, and 0 for lambda greater than 2a. Okay, so there's a certain range minus 2a to 2a where all the eigenvalues are, and outside of that the eigenvalues are 0. Okay, this is in the larger limit, and where a is also given in terms of the coupling constant. Okay, so a has a specific formula, 24g square root of 1 plus 48g minus 1. Okay, so there's a very specific formula. There's a meaning of why they're confined like that, because this potential basically says that the eigenvalues, look at this here, the eigenvalues are attracted towards lambda equal to 0 if g is positive. If g is positive, it's a potential like this. Right? It's a quartic potential, single well potential, so they're attracted towards this thing equal to 0. But these are things which repel the fermions. It's called Coulomb repulsion. Okay, and so as a result, there's a competition. Okay, so there's a crowding of eigenvalues here, and so on. But there are some eigenvalues which are pushed back, but they're pushed back only finitely up to some extent. Okay. Then you can have fun with other models in which you have you give higher powers and so on and so forth. Then it's not just one interval which is populated, but there are other intervals which are populated because it's a multi-well thing. So this is something that I had computed, and so anyway, with this, what can you do with the solution? So let us say you can compute now m to the power p1, m to the power p2, trace of m to the power pn, m to the power pn. How much time do I have? 16 minutes, perfect. Okay. Let's compute this, okay? Which becomes rho of lambda 1, let's say. Let me just take 2 of them, okay? Lambda to the power p1, integral over lambda 1 and rho of lambda 2, lambda to the power p2, integral over lambda 2. So I have just taken only 2 of them. It becomes this, right? What does this angular bracket mean? That I'm supposed to put in this e to the power minus n square s of rho and integrate over rho and divide by the partition function. That's what I'm supposed to do. But you see, because I'm doing large n, it basically becomes this stuff with this integral gone in the large n limit. In the large n limit, that's what happens. I'm doing saddle point, so therefore this is gone, and this is replaced by this. So as a result, it just becomes a product. So first of all, observation is that this is what would have been if you just computed the 1-point function of this operator, trace of m to the power p1, right? So therefore, this is this famous large n factorization. Invariant things, the product of invariant things factorize in the large n limit, okay? You could try to do what the corrections are here, like the 1 over n corrections to this, to the failure of factorization by how much. You could do that. Indeed, you could do that by, not in this model. In this model, there are some subtleties about computing 1 over n corrections, which I can give you 5 lectures on. But in the Gross River model, for example, you can actually do this, and it is done. It is routinely done. So there's 1 over n suppression of the connected diagrams. Okay? So otherwise, in the large n limit, it's just a product of 1-point functions. Okay, and you can compute this now because rho naught of lambda is known.
I have just one question.
Yeah.
So for this to be like split like that, we have to also have like the splitting of z in the denominator.
Oh yeah. No, so z is okay. Good that you said it. Z just becomes e to the power minus n square. Is like that. So I forgot to cross it out. So 1 over z just gets rid of this. That's it. So it just becomes a product of these two things. And these two things by themselves, by the same sequence of logic, it just becomes a product of two things. So this is what is called large n factorization. It's an important concept, large n factorization. And you can compute corrections, plus corrections, which will typically go like some power of n. All right, good. So that's one thing there. So this is what it does. Now, suppose that I'm computing trace of m to the power 4 or something like that, okay? So that's this, trace of m to the power 4, like that. And the theory has quartic vertices, okay? So this is my operator. This is my operator. And, you can define this operator with some 1 upon n, that's like that. And you can compute you can compute just the one. Let's compute just the 1-point function of trace of m to the power 4 in that theory. Okay. Without using any vertices at all, I could just contract them by using the propagator. Okay. So it will be just the 3 so n cube, because we know that it has 3 index loops, and I have defined the operator, excuse me, so I have defined the operator with a factor of 1 upon n, okay? So then it's like n square, okay? So that's that. Now, however, you can use the vertices, you can use the vertex, which has g in it, as many times as you wish, okay? And when you have taken the infinite number of insertions of this quartic vertex, okay, then what you get is this stuff. So take this and multiply by lambda to the power 4, and you do that, and you do series expansion in G, and compare with what you get from Feynman diagrams. And this has been done in up to 4 or 5 orders, whatever, in G, in the Brezhnev and Parisi-Zubair. Okay, let me now say the other things completely qualitatively, because this is how, so this is a very influential paper in the large n physics, where explicitly, so Rajiv, you are answered now, how in this model, this A0 of H is computed. The planar diagrams with arbitrary number of insertions of the lambda. Okay, this lambda is the G here. Okay, you can expand this. You can expand this in powers of G. You can expand this guy in powers of G. and rho naught of lambda will be known in powers of g, and but the exact thing is also known, right? Okay, good. Now, there's a, you can do this, of course, Hermitian matrix model, etc., which was first done here, okay, does not, I mean, there's a different model which was done soon after by Gross-Witten and Wadia, which is two-dimensional lattice gauge theory. And there, you know, so this is a two-dimensional lattice. Okay, I don't have really time to do this stuff, but let us say that these are the links of this, the up links I'm calling by odd numbers, and these are 2, 4, 6, etc., etc. And let me call this 2 prime, 4 prime, 6 prime, and so on. And it repeats like that, up and this way. Okay. Now the action is given by sum over all plackets. These things are called plackets, and they are given by the product of little Wilson lines along these links and so on. I don't know how much of these things are known to you guys, but 2 prime and 1, right? And now I can use a gauge. This is a lattice gauge theory. I can use a gauge which is equivalent to say, so let's say this is time, Euclidean time, and I can choose A0 equal to 0 gauge, which puts all of these links to equal to 1. So all the odd, sorry, I did something wrong. Yeah, so all the odd fellows are put equal to 1. They're gone like that. And the U's are directed fellows. So this was that way. So if I always use right moving U's as my U's, then it will be like U to dagger. So now the path integral is given by product over all links, And now you can make a change of variable, okay, from the U2, U4, etc., to and the upstairs, etc. Believe me, it can be done to these variables, W2, and then similarly W4, etc., etc. So this becomes like product over all the W's, which are simply U dagger, U dagger, U dagger, U dagger, etc. Okay, it can be done. And now it's a, but now they all become decoupled because this fellow has nothing to do with the neighboring plackets and so on and so forth. They all become, they are decoupled, and it's given by just the, so this is finally just W2 plus W4, etc., and their complex conjugate. This is what the action is. Okay, so that's the action. Now it becomes like, okay, good. This is all the W's, but they are all decoupled. Therefore, you can just look at a single placket. So it becomes a single placket problem to the power the number of plackets as a volume. Okay, so therefore it becomes, this is a unitary matrix. Okay, this was a unitary matrix, this is a unitary matrix, so therefore W is also a unitary matrix. So now it becomes like a two-dimensional lattice gauge theory, therefore boils down to an integral over unitary matrices. Now you have eigenvalues which will go on a circle instead of real numbers, so on a circle. And now the corresponding action. So again, some n square will come here, and s of rho of theta will be given by with the action. The action is just so this s of w is just w plus w dagger. Okay, where now I go to this eigenvalue e to the power I theta n. Okay, so sorry, excuse me. There's a trace there's a trace, sorry, so there's a trace like that. So this and W dagger, of course, is a e to the power minus I theta 1, etc., etc. So the trace of W plus W dagger will give you rho theta cos theta d theta. Okay? Cos theta, because it's cosine theta 1, cosine theta 2, blah, 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 up to cosine theta n. So it's like that. And good. And then similarly, because of going from the, so there were these angles, and then will the Jacobian again. So it will be like a Coulomb gas on a circle. Okay, and so the final formula would be, sorry, so this is Yang-Mills theory. So there is a lattice gauge theory, whatever. So there's a factor of 1 upon lambda that will hang around. So finally, the thing will be 1 upon lambda cos theta. So rho theta will be multiplied by this, and then there will be a factor of rho theta prime, rho theta prime, log of sine theta minus theta prime by 2, this way. Probably missing some sign here, but anyway, this is some potential term which tries to attract you towards theta equal to pi, because there is maximally negative. Cos theta is maximally negative at theta equal to pi. So it tries to, so let's say this is, this is theta equal to pi, and this is theta equal to 0. So in the limit, when this thing is very strong, so let's say lambda going to 0, okay, then it just becomes like a delta function. Okay, so this is what is called the weak coupling, the weak coupling behavior of the eigenvalue density. It's like a delta function, and it has beautiful meaning in terms of confinement and deconfinement, etc., etc. I can say, tell you these things at lunch. And the other limit. So here, so rho theta becomes like a delta theta minus pi, like that. And the other limit is lambda going to infinity. Okay, so that's just this. And in fact, if it is not quite 0, but it is, so this kind of a behavior, okay, all right. It's not quite 0, but very small. Then it's a small arc which is filled by eigenvalues. Okay. And on the other hand, in the lambda going to infinity limit is a repulsion that is there, and the repulsion, what does it do? So there are n eigenvalues which are mutually repelling each other on a circle. So what can happen? Uniform, exactly. So it becomes uniform. So so it just fills out the entire circle, and it becomes uniform. Sorry, I'll just make it. Good. Right. Okay. In the last 1 minute, let me tell you one. Unfortunately, I couldn't do the Gross-Devo model. It's really, really beautiful. But anyway, never mind. So there's a very nice physics understanding of this thing, rho theta equal to. Let us imagine that you are computing the trace of W, okay, in this phase. Okay, so that will be like rho theta e to the power I theta d theta, right? So this will be 0, right? So not in this model, but in some other model, a 4-dimensional gauge theory model, where again the model reduces to just eventually one unitary matrix that corresponds to what is called the Polyakov loop. Okay, so that's like the world line action of a quark. Okay, so that this equal to, so this object is like the worldine action of a free quark, external quark, okay? Because I'm talking about here a theory which has adjoints only, okay? These are matrix things. Okay, I'll just finish. So so this means that, you know, the free energy of a quark becomes, isolated quark becomes infinite, okay? So that corresponds to a phase where quarks are confined, okay? No isolated quarks. So the expectation value of the Polyakov loop is 0. So this is not in this context, but in that context, this W is like the expectation value, W is like the Polyakov loop. And Polyakov loop is what? Is a static, a very heavy static quark, okay? And that's not moving anywhere. So its world line is entirely, okay, so world line would have been straight up in time. But I'm talking about here a finite temperature theory. In a finite temperature theory, the world line will be a circle, okay? So the Wilson loop around the time-like circle is what is called a Polyakov loop, and that will be equal to 0. And so therefore, it's a confined theory. On the other hand, if it is like this, okay, then you do the same thing with this delta function, it will be 1. So the isolated, the free energy of an isolated quark would be just 0. Okay, so you can, you know, at will create isolated quarks. So you're in the deconfined phase. So in the middle, you know, when you have sort of tuned this temperature from large to small, somewhere you got the confinement. Sorry, so I should not take this thing too literally. There is a temperature. Okay, so when you take the temperature from 0 to infinity, somewhere the phase transition happens from the confined phase to the deconfined phase. And the structure of the calculation is pretty much similar. And so I should just say that you should study the Gros-Neveu model, which I didn't have time to. All of these things are, much of these things are there in, there are many, many reviews, but I have given 9 lectures. So this is 9 lectures compressed into 2 in around, I think, 2012 or something like that. But I have added some few more things here. So you can look at my SCRC lectures. But of course, you should certainly look at the original articles, no doubt about that. Thank you, I'm done.